property number 5. If A1, A2, A3 dot 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 are in F, then okay. So, this is a very important property. Okay. This says that, so you have a countable set of events. So, right, A1, A2 dot dot dot, it is a countable collection of events, and of course, the countable union is also an F, right, because F is a sigma algebra, right. So, this is well defined. So, we are saying that the probability of a countably infinite union is the limit of the probability of an event, this countably, this finite union, right. So, what is on the left is the probability of a this is the probability of a countably infinite union, and you have here a finite union and a limit, right, and we are saying that these two are equal. Okay. So, it looks as though there is nothing to prove, right. It looks like, so what you are doing is like you are in very informal terms, you are just taking the limit inside, right. So, in that sense it looks like, so this property is known as continuity of probabilities. Okay. Continuity of probability measure, that is what this property is called, for obvious reasons, right. This looks as though you are simply, so if you have a continuous function, you take the limit inside the function, right. This looks as though you can just take the limit inside, right. That is why this is called the continuity of probability measures. This is a highly non trivial statement. Okay. This is by no means obvious. Actually, it takes some serious thinking to even understand what this property means. Let me explain. So, first of all, I told you that this kind of a union, countably infinite union, should not be thought of as a sequential operation. It is not like unioning, it is not like you are unioning A1 with A2, then A3, then A4 and so on. That is not the way to look at this, right. This is there in the, I think I made a remark in the set theory notes, right. This should, what is this? Set of all omegas in at least one of the AIs. So, please do not look at this as a some kind of a limiting version of some finite union, right. After all, right, I mean, what is the limit of a set? There is no such thing as, we know limit of numbers, right. So, this is not like, you cannot say, oh, this set is like the limit of that union or something like that, there is no meaning to that, right. That is the first clarification I want to give, right. So, this is the set of all omegas in at least one of the AIs, and this is the set of all omegas in A1 through AM, at least one of the A1 through AMs, and so that is a probability. So, you can look at let us say this as a function of, this will be some, call this some PM, right. These are numbers that depend on M, right, you are unioning the first M, right. So, this PMs are, so I claim that this PMs are monotonically increasing in M, that is clear. Why? AM is contained in, so well, okay, this union is contained in the M plus 1 union, right. So, you can say that this PMs are monotonically increasing sequence, right. The limit of a monotonically increasing sequence has to exist, right, it has to converge. So, this right hand limit exists as some real number, right, and left hand of course is well defined, right. It is some probability of this countable union, countably infinite union, which we know exists because this guy is a element of the sigma algebra. So, this must be well defined. So, this property is saying that this number which is well defined is equal to some other limit which is also well defined, right, and but it is by no means obvious why they are equal. Okay. In particular, it is not like you are taking the limit inside, it looks like it, but it is not that. Okay. Yes.
I think you made a wrong statement here in the sense you said limit of a monotonically increasing sequence has to exist.
Yes, it well no, yeah. So, this is correct. So, this is a monotonically increasing sequence. So, it has to converge, right, it has to converge to something, right, it has to converge to either a real number or plus infinity, right. So, this Pm exists, this Pm is well defined, right. I am saying that this limit is equal to another entity which is well defined, right, it is another probability, right. So, in particular, see, if you look at these Pms, they are after all bounded above by 1, right. So, in this particular case they are just probabilities, right. So, it will be bounded above 1. So, it has to converge, it cannot converge to plus infinity, right. So, if these were ordinary measures, this is still true, except that this limit may not be finite, it might be plus infinity, right, correct. Okay. So, is the statement at least clear? The proof is non trivial, but is the statement clear? Okay. So, this do not take this lightly, this is not a simple assertion, right, this is by no means an obvious property at all.
These disjoint or
No.
do they need to be disjoint?
Have I said that? No, then they do not need to be, right. Any other questions? Okay, let us prove this. So, let us prove, okay. I am trying to prove this now. Proof define B, okay, let us do this. Define B1 is equal to A1, B2 is equal to A2 minus A1 and so on, right. So, that Bn is equal to An minus so An minus union Ai I equals 1 through n minus 1, okay, and so on, right. So, I am defining so I have these Ai's, this is a countable collection of events. So, I am defining another countable collection of events namely Bi's, okay. So, I do that. So, I keep A1 B1 as A1, then B2 I define as A2 minus A1, B3 will be A3 minus A1 union A2, right, and so on, right. This is another countable sequence of events, okay. Now, what can be shown? So, this is a very important step, okay. This is a very important step in the construction. So, what you can show is that claim Bi's are disjoint. I.e., Bi intersection Bj equal to null for all I comma j greater than or equal to 1. Okay. So, it looks intuitively obvious, right, except you have to prove it. Okay. that is a homework. Okay. Proving this claim is a let me call this claim 1. Okay, this claim 1, proving claim 1 is a homework. It is simple enough, but you have to be careful, you have to do it properly. Okay. It is not difficult. So, you start off by assuming without loss of generality is that j is bigger than I. Okay, I give you a hint, assume j is bigger than I. And you can prove it by contradiction, assume that there is a common element to I and j and arrive at a contradiction. Okay. Okay, this is one claim. The other claim is the following. I am claiming that union I equals 1 to infinity, well I equal to 1 to infinity or so I want to claim that union I equals 1 to infinity A I equals union I equals 1 to infinity B I. Okay. This also you will prove. Okay. So, how will you prove that these two sets are equal?
This is subset of that.
Correct. So, if whenever you have to prove two sets are equal, you have to say that any element in this union is also in this union and vice versa, right. So, if any omega is an element of at least one of the A i's, it must be an element of at least one of the B i's and vice versa, right. You prove that you are done. Okay. And so, I think you can also prove, and you can prove that the finite unions are also that is also true. Okay. So, what is this union? This is the union of events in A1 through A, this is the union of elements in A1 through AM, and similarly for this you have to prove that this is contained in that and that is contained in this. Okay. So, these are all simple exercises you will do. Okay. There is nothing very great about this, but you these are like lemmas in proving this result, okay, claims. Now, we can prove it, I think. Now, we are ready, because I can write. So, this is what I want, right. On the left hand side I have probability of that guy, right. Now, that is equal to probability of this union. Now, why is this union much better than that? These guys are disjoint, B i's are disjoint, A is may be very complicated, right. They may all be intersecting in very complicated ways, but B i's are disjoint. So, I can use what property? Sorry, countable additivity, right. So, let us do this now. Probability of union I equals 1 through infinity A I is equal to probability of union I equals 1 through infinity B I, that is because these two are equal, and this will be equal to sum over I equals 1 through infinity probability of B I, correct. Everybody okay? This is because of B i's are disjoint and countable additivity of probabilities, right. So, now, so I am now in a good situation where I have, so I had this probability of this countably infinite union. Now, I wrote it as a summation. Now, this infinite summations are in fact just limits of finite summations. See, these countably infinite unions are not limits of finite unions, that is not true, but summations this infinite summation is the limit of a finite summation, right. So, this I can write as limit m going to infinity I equals 1 through m p b I, correct. Everybody happy? This is just by definition of this summation. Okay. Now, again what will I do? This I can use finite additivity, right. So, now I can write this as limit. See, after all I want to maintain limit on the right, right. So, I brought out a limit on the right. So, so I should maintain that limit, right. I should not get rid of it. So, I should maintain that limit and then I will write this as probability union I equals 1 to m b I, which is equal to, yeah. So, because of this, right, which is equal to limit m tending to infinity probability of union I equals 1 through m a I. Okay. So, this is a fairly non trivial proof, right. So, you have to be very careful. So, this is by claim 2, right, this equality is by claim 2, this equality is by finite additivity, right. This is by definition of the infinite sum, right, and this equality is by axiom, right, the axiom of countable, this is by countable additivity. That is by countable additivity and that is by claim 1, claim 2. So, this is by countable additivity and claim 1, right, clear. So, this is something we will use repeatedly. Okay, this continuity of probability measures is this is a non trivial property, but from now on we will be like happily taking the limit inside. Okay. It is as though we are taking the limit inside, but there is some serious proof involved, correct. Any questions? Okay. So, I will now state two more properties which are in fact corollaries of this continuity of probabilities theorem, but they are also important in their own right. So, I am not going to, I am going to state them explicitly. Okay. This is property number 6, right. If A1, A2 dot are nested increasing events, i.e. A1 contained in A2 is contained in A3 is contained in and so on. Then probability of union I equals 1 through infinity A I is equal to limit m tending to infinity probability of AM. See, this nested increasing event means, so A1, then A2 is bigger than that, then A3 is bigger than it contains A2 and so on, right. So, there is this nested sequence of containments. If you have this situation, then this is actually nothing but a very easy corollary to the previous result. So, in this situation we have union I equal to 1 through m, A I will simply be AM, because AM is the biggest guy, right, and the other guys are all smaller, they are all contained in them, right, fine. So, this is a very trivial corollary. So, limit m tending to infinity, this term simply becomes probability of AM, right, this finite union is equal to AM, right, very easy corollary. Any questions? And similarly, so for intersection you get a similar result, which is probably most useful. So, I will also state that explicitly. Property number 7, if A1 A2 dot 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 are nested decreasing, i.e. A1 contains A2 contains A3 dot dot dot. Okay. So, these guys are now nesting in, right. So, AN is contained in AN plus 1, or we say it the other way, AN plus 1 is contained in AN, right. So, that is this. Then probability intersection I equals 1 through infinity AI equals, any guesses? Limit m tending to infinity, probability of AM. How do you prove that? Intersection will be, sorry. So, I want to prove this result. How do you prove it?
Intersection of A1 to AM will be AM.
Intersection of A1 through AM will be AM, right, that much is clear, right, because of this containment. Then what? Actually, you can do that too, right. You have to see, you are dealing with intersection now. So, you have to do what? Somewhere you have to do De Morgan, right. You have been going from union to intersection, you have to do a De Morgan. Actually, do a De Morgan on this result, you know. You do a De Morgan on this, what do you get? A1 complement will contain A2 complement. See, if A1s are nested increasing, then the complements are nested decreasing, right. So, use that property and use De Morgan, you will get it, okay, fine. So, these are actually fairly simple corollaries of the continuity of probabilities. So, actually this form is probably the most useful, okay, where you have this decreasing sets, right, these nested decreasing sets which are contained in with one within another, and this is a countably infinite sequence of nested sets, right. So, these sets are colloquially they are called Russian dolls, okay. So, have you seen Russian dolls? They are actually dolls. You open one doll, there will be another doll, open another, like they have this bunch of dolls inside one another, right. This is like that, right, except there is an infinity of them, okay. So, these kind of nested decreasing sets are called Russian dolls, okay, that is, and then you have this property for Russian dolls, okay. Okay, any questions? The next property is property number 8, is an important property called the union bound. Says that if A1, A2 dot dot are events, then probability union I equals 1 through infinity A I is less than or equal to sum over the probability of A I's. Okay. So, this is an important property that says if you have any arbitrary sequence of events, then the probability of the union is less than or equal to the sum of the individual probabilities. All right. So, essentially this says that, so in adding up all these probabilities you are over counting, right. So, this says that this will be bigger than this. Okay. So, if A's are disjoint, of course we know from the axioms that equality holds, but if A's are not necessarily disjoint, then the probability of the union, countable union, is less than or equal to the sum of the individual probabilities. Okay. This is always true, but note that what is on the left hand side is a probability, whereas what is on the right hand side may be something bigger than 1. Right. This is just a summation, right. This is a summation of non negative numbers, this may in fact be infinity, or it may be some number bigger than 1. So, this is always true, but it is useful only when the right hand side is less than 1. Okay. So, the way to prove this is to just again go back to your BI's. So, remember we defined BI as AI minus union j equals 1 through I minus 1 AJ, right. And we know from our earlier claims that union of AI's is equal to the union of BI's, right. So, I can take the left hand side and say that probability of what is on the left hand side is equal to the probability of union I equals 1 through infinity BI's, but by construction we also argued that BI's are in fact disjoint, right. So, this is a countable union of disjoint events, right. So, this will be equal to sum over I equal to 1 to infinity probability of BI. So, this is because of countable additivity of probability measures, right. BI's are disjoint. Now, notice that BI's are, so for every I, BI is contained in AI, right. That is because BI is defined as AI and then you remove something, right. So, this BI for every I, BI is contained in AI, right, which means that probability of BI is less than or equal to probability of AI for all I, which means that sum over I equals 1 through n probability of BI is less than or equal to sum over I equals 1 through n probability of AI for all n, correct, for all n greater than or equal to 1. Therefore, by now you send limit n tending to infinity, you will get that this summation here is less than or equal to the, then you will get this infinite summation probability of AI. Okay. So, that gives us the proof of the union bound. Now, so a remark on the converse. So, you know that if AI's are disjoint, this equality necessarily holds, right. The union bound holds with a equality if A is a disjoint. However, it is not quite true that if equality holds for certain events, it is not necessarily the case that A is a disjoint. Okay. So, what you can show is that if equality holds in the union bound, then the intersections between A and AJ will have 0 probability measure. Okay. It is not quite true that they do not have any elements in common, they may have elements in common which have 0 probability measure. Okay. So, the converse of the union bound is not completely, it is not quite true. Okay. So, the union bound is used in several applications. So, we will see an application in the Borel cantilever lemma, but also in digital communications. If you are transmitting a set of bits, the probability of, let us say AI is the probability of the ith bit going wrong, for example, you bound the probability of making some error at all by adding up the probability of each bit being decoded incorrectly, and if this decode this each of these probability is small enough, this union bound can actually give you a quite a useful estimate in digital communications. Okay. And it has several other uses as well. Thanks.